Given a collection of points in 2, 3, or higher dimensional space, a best-fitting line can be defined as one that minimizes the average squared distance from a point to the line. The next best-fitting line can be similarly chosen from directions perpendicular to the first. Repeating this process yields an orthogonal basis in which different individual dimensions of the data are uncorrelated. These basis vectors are called principal components, and several related procedures, principal component analysis, PCA. PCA is mostly used as a tool in exploratory data analysis and for making predictive models. It is often used to visualize genetic distance and relatedness between populations. PCA is either done by singular value decomposition of a design matrix or by doing the following two steps. 1. Calculating the data covariance or correlation matrix of the original data. 2. Performing eigenvalue decomposition on the covariance matrix. Usually, the original data is normalized before performing the PCA. The normalization of each attribute consists of mean centering, subtracting its variables measured mean from each data value so that its empirical mean is 0. Some fields, in addition to normalizing the mean, do so for each variable's variance, z-scores. The results of a PCA are usually discussed in terms of component scores, sometimes called factor scores, and loadings. If component scores are standardized to unit variance, loadings must contain the data variance in them. If component scores are not standardized, then loadings must be unit scaled, and these weights are called eigenvectors. They are the cosines of orthogonal rotation of variables into principal components or back. PCA is the simplest of the true eigenvector-based multivariate analysis.